All right, so we're really going to dig in into some examples using integration by parts. And recall that our integration by parts formula is that the integral of u dv is equal to u times v minus the integral of v du. So that's going to be key to all of these examples. So the first one that we're going to look at is the integral of x squared e to the 2x dx. And I mentioned in the last video that typically when we're making our choices for u and dv, if we have a product of a monomial, so x to some power, times a function that's not going to disappear when we differentiate it, e to the x, sine x, cosine x, etc. We're typically going to choose the monomial for our u because differentiating it is going to knock it down a degree, and then we'll choose the rest of the stuff to be our dv, because that's pretty much going to be the same thing up to a constant whether I differentiate it or integrate it. Okay, so we're going to take the differential of x squared, so that's going to be 2x dx, and then when we integrate e to the 2x, I'm not going to bother with a u substitution here because I feel like it's just a little too clunky with all the integration by parts. But basically you're doing a u substitution with the 2x, and then the chain rule would apply, right? So if I were differentiating e to the 2x, I would have to multiply by 2. Since we're integrating, we're going to divide by 2. And you can work that out on your own if you need to check. So I'm just going to write my v as 1/2 e to the 2x. Hopefully we feel okay about that. If not, pause the video and double check for yourself. Now remember, I'm not going to add a plus c at this point. I'm just going to wait until the end and add a single constant for the entire original integral. Okay. So let's apply our integration by parts formula now. And so I can write the integral of x squared e to the 2x dx, so integral of u dv, as u times v. So I'm going to think about this as x squared times 1/2 e to the 2x minus the integral of v du. So that's 1/2 e to the 2x times 2x dx. Now I'm going to simplify this just a little bit, make it look a little prettier. So I'm going to write this as 1/2 x squared e to the 2x. And here I'm going to let the 2's cancel, and I'm going to bring the x out front. So I'm going to write this as x e to the 2x dx. All right, well, notice now we have a problem very similar to the one that we had in the last video. So what I'm going to do is I'm going to take this integral and I'm going to do integration by parts again. So here I'm going to choose x to be my u, and I'm going to choose e to the 2x dx to be my dv. Notice you're always going to have dx attached to the dv, right? Because that is a differential expression. So then du is equal to dx. My v, again, same thing, is going to be 1/2 e to the 2x. So now I'm going to rewrite. I still have this 1/2 x squared e to the 2x here. And I want to be careful that I'm subtracting the entire expression that I'm replacing this integral with. So I'm going to put a set of brackets in here. All right, so the integral of u dv is equal to u times v. So x times 1/2 e to the 2x minus the integral of v du, so minus the integral of 1/2 e to the 2x dx. And I'm going to distribute this negative and simplify a little bit. So we're looking at 1/2 x squared e to the 2x minus 1/2 x e to the 2x minus a negative gives us positive integral of 1/2 e to the 2x dx. And now finally, this is a very simple integral to compute. And so we have 1/2 x squared e to the 2x minus 1/2 x e to the 2x. And integral of e to the 2x we know is a half e to the 2x. So multiplied by this 1/2 constant that we already have gives us a 1/4 e to the 2x. And then finally, we're going to add our plus c. More examples in the next video.